conference going on. Hardly I see students. Okay, so up till now, what we did, any queries, any of you? We'll finish with one topic and then we'll start with BJT. Right, last time we did an example. I'm audible properly? My volume is low or it's okay? Yes, you tell me. And I don't listen to anybody. Am I audible? My screen is visible properly?
Yes, ma'am.
Okay, very good. So last time we ended up here, and if you don't have any queries, then with your permission, I would like to go ahead and start this next topic. Different kinds of diodes with different applications, and we have seen many of them. Right, and these are main highlights of the diode applications. And one more application that we are going to see today is using diode. You can make a doubler, tripler, 3 times, 4 times of the voltage. Okay, but you must understand that this is the law of conservation of energy, that the power at the end of the day remains same. So if the voltage is doubling or tripling or 4 times, the current decreases. Okay, so at the end of the day, the power remains same of the circuit. When you calculate the power, P is equal to V into I, it will remain same. But there are applications. Okay, so these applications are where you need high voltage. So let's say in your cathode ray tube before the TV that was using CRT, right? Cathode ray tube, where it will need high voltage. So there, and then you have laser systems, X-ray, right? And then in your LCD TV also for backlighting. So this, if you understand how LCD screen works, right? So you need double, triple the voltage. We use such circuits. Then, of course, in power supply, in oscilloscope, when you are giving a voltage, higher voltages, right? So these are such diodes are used. And if you know particle accelerator, you must have heard of. So since in particle accelerator, so since 1930s, such circuits have been used. Okay. And another good example is iron pulp copy machines. So in short, everywhere wherever you need higher voltage, and especially particle accelerators are, if you know the study of God particle, right? So this the system requires very high voltages. So how to generate that? So that's where this thing comes. As I said, power remains same. The other way of doing is using a transformer. Okay, but that transformer, as you can understand, it's heavy, it takes space, it's expensive also. If you want, as I just mentioned, that in your LCD TV also, in your CRT, the TV that was using the CRT cathode ray tube, right? Of course, we need that, and they are outdated now. But if a transformer would have been used, then it would have been more heavy, space occupying, and expensive. Today, TV are light. So same thing if you want to do and replace the transformer, then diode, because step up, step down you can do, right, in the transformer also. But here diode is a better option. And as you can see, these circuits are simple. Basically, you have a diode and a capacitor. And we are going to understand this circuit today. I'll use the pen only because that will be easy rather than the pointer here. So let us start with this doubler circuit. And what it basically does is that there's a sine wave as an input, AC signal as an input. And what you get is if this is plus minus Vm, right, in the doubler, you will get a DC signal. So this is almost pulsating DC, right? And that is twice this. Okay, so 2 Vm. In case of tripler, you will get a 3 Vm. So the input is an AC, the output is DC, which is twice or thrice the peak amplitude. Okay, so that's the goal. And let's see how to build that. So as you can see here, It's a capacitor, and then the diode connected. The polarity of the diode is such, so C1, C2, and then D1, D2. And this is the terminal through which you will get the output of across the C2, the output voltage we will take. Now you must understand that this circuit, this is as an input. Okay, so this can be, as I mentioned, this black box can be any application, a power unit also, or as I explained you, couple of oscilloscope or whatever. So this will be given. A circuit can be replaced by a resistive load, you can say. So in practical circuits, there is an output which, if I want to show here, it can be replaced by a resistive load. So I can just replace this with a resistor here. Okay. So this can be replaced. So across this, I mean, right? This is connected, and then you add a resistor, right? So that is your next stage, equivalent, the input resistance of the next stage, this R. So this is the practical circuit. And up to here, up to this part, all this part is your doubler. So with that thing, right? So with that thing, let us understand. And as I have always been telling you, first thing what you will do is to analyze the circuit. What you will do, you will talk of this first positive half, and then you go for negative half. Okay, so we'll start with the positive half of your waveform. And what you will see when you say positive half, I can write here plus and minus, right? So this is plus and this terminal is minus. I can do that. And when it is at the peak, right? So when so positive half, this diode is forward biased or reverse biased?
Forward bias.
So this is forward biased and this guy is reverse biased. Okay, so because of the polarity of the diode, the way it is connected. So now if this is forward biased and this is reverse biased, so this loop is not existing, this two for now. And since this is forward bias, the direction of the current will be this, right? You agree. So this is the way the current flows. Agreed or no?
Yes.
Yes. So now if this is plus and this is minus, so now the current is flowing and it is charging this capacitor with the polarity plus here and minus here. So this is, you are giving a potential at this plate. So the positive ions collect here, and then accordingly the negative ions will collect here, and it will charge to this peak value, this capacitor, right? So it will charge to the peak value, and if the peak is Vm, it will charge to Vm with this polarity plus and minus. Is that okay?
Yes, sir.
Very
Yes,
good.
ma'am.
Very good. So now we'll go step by step, and remember, if it is asked in the exam, you have to explain this step by step. You just can't just write out something then like a story ki input ye denge output ye niklega. The output we know kaise, what is the polarity, how it works, that is very important. If you don't write, you will get big zero. So now in the negative half, so when it is minus and plus now, okay, and as you can see, this guy has already charged to plus and minus. So in that case, D1 is forward biased or reverse biased? When it's a negative half,
Reverse bias.
D1 will be reverse biased. Okay, so D1 is reverse biased because of the polarity. Because see, this is positive, this is negative, and this negative is now positive, and here also there is already, so the because of the way it is connected, it is already reverse biased, and now this is forward biased, right? Because this is plus minus, and here it is minus, and with this plus, this is forward biased, and the direction of the current is going to be right, and this is like not connected. So the current will flow because this is the direction arrow of the diode, right? So this is the direction, and it will flow from here like this way. Agreed or no? So now this is minus, this is plus, and the polarity of this will be plus here and minus here. Agreed? Of this capacitor, a plate plus, to a plus outside. Okay, that is that simple only. If you have two plates of a capacitor, right? And when you give a positive voltage here, right, this plate will be positive, and here you will have negative ions. If the positive is here, this will be positive, this plate. Whatever voltage you give, that will be the plate, right, polarity. So if it is plus here, then this is plus and this is minus here. Agreed or no? But what is the voltage here? What will be the voltage here? So please
Two times the
what is yes,
VM.
why two times? Because this is already so now this is when it goes to the peak here, negative peak. It is VI, and so this capacitor will charge up to the peaks. After one or two cycles, now it will give you. I will just explain it. So yeah, so this is minus plus minus plus. So this is now two times, okay, VM, and with this polarity. So this is plus and minus, and this is 2 VM it will charge, because 1 VM and this is another VM, and hence it will be 2 VM with this polarity, minus and plus. We can always invert the polarity, that using transistor I will show you. Okay, so that polarity is not a big deal, although it will come in the negative one, but we can invert it and we can put it in a positive, this direction here. So 2 VM. So the voltage here with this polarity, yes, it is negative, but as I said, a simple circuit, we can invert the polarity, and we can have this 2 VM here. So this is twice the voltage as just explained. And what you see here now is, if there would have been no load, because see, this circuit is made for some it is given, this output of this circuit doubler is given as an input to another circuit, which can be represented by its input resistance here, R. So with this R, you will have this kind of waveform, because the capacitor will charge to the peak and then it will discharge, because if there is no R, it will not discharge, it will show you the straight line as we had seen before. It will be the straight line, but the practical circuits, it is always as a load. The circuit is as an input to another circuit. So as I explained you. So what happens is that in the positive half, when this was reverse biased, right? In the positive half, this is charging, this was reverse biased. So this capacitor, which was already charged, it didn't get a path to discharge. So what it will do, once there is a load here, it will discharge through the load. Okay. So it will discharge through the load. So this is during the positive half, it will discharge a little. And that's what it is discharging. And that RC time is always greater than the T of this. Yeah. So this one period is having a time period of T. Then so it will discharge but little. Otherwise, if that RC is very, very less, then it will discharge fully and it has to charge. So you will not get the output almost DC, okay? And this can further be filtered, and using voltage regulators and a diode and all, you can get a pure DC, right? And with large RC, we can have almost DC-like waveform. So during positive half, when this is charging and this is open, this is not working, this diode is reverse biased, this capacitor, which was already charged, will get a path, and hence you have this discharge. After it has charged, it will discharge also. And because it has discharged, again it will charge and then again discharge, so on. So is that clear to all of you?
Ma'am, I'm having a doubt, ma'am.
Bolne?
Ma'am, why the in the negative half of the input, when the resistance was not connected, why this C1 was not discharging? C1 is also discharged, right, ma'am?
Just 1 minute. What you are telling me, let me understand. So in the negative half, you are asking that this is not discharging.
Yes, but it should discharge now, because
See, this is discharging in the positive half. In the negative half, it is discharging this guy. That's why this is charged to 2 VM. See, let me explain you again. Positive half, all of you understood, right?
yes, ma'am.
Okay, so now in the negative half, see, negative half means this was in the positive half, this was plus, this was minus. Can I put that? Positive
Yes,
half plus minus the VM, it was charged to VM, this capacitor. You accept that, na? Positive half though.
Yes, ma'am. Yes.
Now you have negative half. So negative half, this is minus, this is plus. Is that okay?
Yes, ma'am.
Yeah. So now, if this is the thing in the negative half, and in that case, D1 is forward biased or reverse biased?
Reverse biased.
Reverse bias in the negative half, so this loop is not there, and this is forward biased. And the current flow is like this. the direction of the flow of the current. Electrons flow in the opposite direction, direction of current flow is this. So if this is the direction of the flow of the current will start flowing from here. So from all over here, it will flow here. Okay, and now what it will then, so this guy is now charging. Now how much it is charging? So already for the negative half, it will start from here, it will reach here. This is the peak. So Vm, so for this voltage already Vm, it will charge, and at the same time, this is also discharging. So this Vm plus this Vm is 2 Vm. That's why it is 2 Vm here. So this has already discharged during the negative half, fully discharged. And when you are done with this negative half, right, this capacitor has no charge. And then when the positive half comes, right, at that time it will start charging again 2 Vm. And during positive half, so because this is, if there is no load, no load, in that case, this will be a straight line. But in case of a load, when there is a positive half and this is open, right, this will get a path to discharge a bit. Do you understand?
Yes, ma'am. Now.
During negative half, this is discharging, and then it will have no charge left, capacitor.
But then the voltage across this C1 will decrease, no, ma'am.
So a negative half from here it will starting negative half to here. So by the time it is starting and ending here, this is also discharging, and when it comes here, when the negative half is done, it will be zero charge. This is the time, this is the interval when this is also discharging C1, and it is behaving like a battery discharging. It is like a battery already charged to Vm, and now it is giving. So this, you can think this too, this is superposition, this voltage plus this voltage together, it is discharging through this, and it is charging. I mean, this is discharging, and this is also your negative half together, it is added, and it will charge this C2. How much? Up to the maximum. So Vm plus Vm, 2 Vm. And then it is, zero changes now set here.
But if you write KPL at the negative peak, then we will get Vm. Yes, Vm minus 2 Vm is equal to 0. That is not possible.
So this is your loop now. This is whole your loop. Yeah. So if you add this is 0. So this is equal to this plus this. Minus. Yeah, polarity is, this is plus polarity, this is minus polarity. This is simple, don't confuse yourself. This has charge during the positive half. And then in the negative half, it is getting a path. So this is getting a path to discharge, and that discharge will charge up this. This is discharging. But yes, where is the charge getting collected? Here. जैसे क्या यहाँ आवश्यक बताओ आनु क्या आवश्यक तो यहाँ चार्ज कर सकते
now
yeah, it is getting a path like you have a canal and now the water is flowing, it is getting a path like that.
Yes, ma'am.
Okay, good. So let us go ahead. Now this is also this is full wave voltage doubler. So here, as you can understand, that this was, so this discharge was happening during which cycle? A discharge, it was during positive half. When this was not charged, this was reverse bias and it was discharging. Okay, so this is during, so this is half wave. So during the half wave, it is discharging. And it is charging also for the half wave. Here it is full wave and the connections are like this, as you can see that the polarity, this is D1, D2, C1, C2, and this is the polarity of this. The polarity is like this. Here it is the reverse of that. And here this is where it is connected. And you have C1, C2, and the voltage is across these two terminal, output voltage. Here what is happening is that, as I said, you start with this positive half. Okay, and then we'll go for the negative half. So during this positive half, which diode is on as per the polarity? So I can write here positive and I can write here negative. In this case, now this, right? So this negative here and this positive here. So which diode is forward biased? So this
D1.
positive is coming here. So E1 is forward biased, right?
Yes.
Yes. And E2 is reverse biased. If this is forward biased, then the flow of the current will flow in this direction or no? And what will happen if the current, because this is the direction of the flow of the current, as I have said in the very first lecture. So now if the current is flowing in this direction and this is positive, this capacitor is going to charge because it is on the way, and it is, this capacitor is like a well, okay, and whatever the charge is coming, it is getting collected there. So this is like a bucket. You can think an empty bucket and the water is being filled up. So this is a bucket capacitor and the charge is like a water and it is filling up this, okay. So this is now positive, and now the polarity is this plus and minus, because this is plus here, this is the positive potential here. And now in the negative half, what will happen? This is forward biased and this is reverse biased, and the direction of the current will be, is going to be this way, right? So this is the direction of the current, like this way. And in that case also, what will happen? This is plus and this is minus, right? Because this terminal, so in the negative half is this, right? So, right, so this terminal is plus and this is minus. So this is forward biased. Okay, and this is plus here. So this is plus, this is plus, this is minus. So now you can understand the polarity is plus, minus, plus, minus. So at the end of this half, this is charged. At the end of the other half, this is charged. And so during both the half, the charging is happening. Okay, half. And when they are connected, this is plus, this is minus, this is plus, this is minus, it adds up. This is adding up here. Okay, so this is adding up here, and that's why you have, so if this has charged to Vm maximum, this has charged to Vm maximum, because of the polarity plus minus, you will have 2 Vm. And as I said, there is a resistive load here. So right, with the resistive load, right, what will happen? It will discharge for both the half. When this is charging, this will get a path to discharge through this R, right? And then when, so and vice versa. So for every half cycle, it will have discharge. So that is this frequency is more here, okay. But this is full wave, means the charging and discharging is happening for every half cycle. In this case, it was for during one cycle it was happening. This is in one cycle it is happening twice. So this is charge and this is charge for the other half. So twice charging and twice means in the first one this guy is charging, in the second one this is charging. So every half cycle that charging discharging is happening, and that's why this is full wave voltage doubler, and you get this kind of waveform. So with that, this is simple. We'll go to this next one, that is voltage tripler. Okay, and be with me on the same line. It's all about the polarity of how these things are connected. Okay, so what you will see here, I would like voluntarily somebody to help me. And it's not that everything should be correct, but at least for the positive half and the negative half, you can help me. And then again, positive half and negative half, right? And what you will see is that these are the connections here in the tripler. You will have how many capacitors? C1, 2, and 3, and then D1, D2, D3. And the voltage is 3 times, okay? So 3 Vm, like this. And this is the circuit. So if voluntarily, and then you can leave your ID in the chat box. Okay, and you will be rewarded. We have to reward you if you reply. So that interactive environment has to be there, and that's why I motivate. Even if you say wrong, you will be rewarded. So it's not about, it's just your daring to speak out and willingness to do, right? So yeah, so during positive half, so you know this input waveform, positive, negative. So during positive half, come on, who will tell me? I want somebody.
Hello, ma'am.
Ah, yes, very good. What is your name?
Bhavya.
Bhavya. You guys are not coming to the institute, right? Your seniors will be there, third and fourth year, and then maybe probably you guys will also have to come. Did you receive any email, Bhavya?
Yes, ma'am. Yeah. So third and
College
नहीं हाँ
आवन?
हमें नहीं मिला email.
अच्छा. So maybe I don't know. They know.
Seniors को आ गया.
Yeah,
Seniors को आ रहा है.
correct. So during positive half, what is happening with C1, D1, and all this?
D1 will be forward biased and C1 will charge to full VM in the positive half. First
So
positive.
okay, very good. So D1 is forward biased, and then because of the polarity, D2 and D3 are what?
Reverse. D2 and D3 will be not be connected.
They will not be there. They are reverse biased, and because of that, the polarity of this C1, it will be charged to plus this. With this polarity, it will be charged to this because this is the direction of the current, right? And this is
Yes.
plus here because of the positive half. So this is plus, this is minus with this polarity. Is that okay with everybody? And remember, here output we are taking across this terminal, and so that is across this capacitor and this capacitor. You add up because of the polarity. They are connected, right? The capacitors, so that their voltages get added up, and we have 3 VM. But let us see, we have just begun with the first half. So now during the negative half,
This C1 and C2 and D2 will be connected. D1 will be reverse bias. D3 will be reverse bias.
so
And C2 will charge to 2 VM.
One minute. In the negative half, in the negative half, who is biased forward and who is biased reverse? That is the first.
D2 is forward bias and D1 and D3 are disconnected.
Yes, you are right. So this in the negative half, these two are like open and this is connected. So because of that, now you can understand that negative is, this is minus and this is plus here. Okay, and like the same thing, minus plus, this will charge to 2 VM with this polarity. This is the direction of the current, right here.
Yes,
So everybody agrees 2 VM up till here?
Yes.
Okay, so this should not be hard to digest. Now main thing comes. During the second positive half, okay, so the cycle is done, positive and negative. So we did up to this point. Now the second half, then what will happen? So after like 2-3 cycles, then you will get 3 VM. Okay, so the first it is charging the capacitors properly. So now in the second positive half, this is plus and this is minus.
I guess D3 will be connected and D1 and D2 will be disconnected.
So now listen,
And
this
it
is
will
the scenario. See, this is the scenario that this is plus, this is minus. Okay, and this is plus here and this is minus here. So because of the polarity, right, this two will be
Disconnected. Reverse bias.
So why D1 will be disconnected? So during the second positive half, diode D3 is forward bias, okay? And D1 and D2 are reverse bias. And D1 is reverse bias because why?
Because capacitor has negative charge.
Yeah, so this is, so here this is polarity. This will not change. It will remain fixed only, right? And this is already charged. So this is minus and this is plus. So this is reverse biased, right? And this is here minus and this is plus. So this is also reverse biased. So this is only forward, isn't it or no?
Yes, ma'am.
Correct. And now what will happen? So this is now forward biased. So let me make this. And this is conducting, and this is the direction of the current. Right? This is the direction.
Yes.
Okay. And so then what will happen?
Yeah, finally, we get 3 VM all over charges.
So what will happen? The capacitor.
C3 will be
C4.
charged. C3 will be charged, and C1 will also be charged.
So this will discharge, no?
Yes, ma'am.
This will discharge. Because now it is getting a path like this. This is conducting. And this is minus here. Okay. This is minus now.
Yes, ma'am.
So here this will be minus, and because this is a minus here, this will be plus here. So what is happening? You just I'm
C1
repeating.
and C3 both
just
are charged to 3 VM, so we will get the final voltage 3 VM.
So now there are two things happening. Yeah. So once again, let me repeat from afresh. During the second positive half cycle, diode D3 is forward biased. Okay, you understand that?
Yes, ma'am.
And D2 and D1 are reverse biased because of the polarity, the way they are connected. That is one thing. And then what is happening here is that as a result, the voltage. So this voltage. It will appear across this C3. Okay, the voltage that is 2 VM across C2. Across the C2 is discharged, and it will flow through this capacitor C3. So this is discharging, it will flow here, and it will charge this C3 to 2 VM with this polarity that is shown. And then this C1 and C3, they are in series, okay? And the output voltage is taken across both of this terminal here through C1 and C3. And since this is the voltage across capacitor C1 is VM, and this is and VM, and this is 2 VM, you will have 3 VM. Okay, so this is how it will be. But if I ask you, okay, this VM here, how did it get VM?
From the battery.
Yes. So from this input, because during the positive half, this path is there now. This path is there. So the current is flowing, as I showed you. This whole loop is, see, these two segments are not there. So this whole thing is not there. This two is not there. Okay. So during the positive half, the flow is like this. Okay, and so this is VM, and this will appear here, and that's how we will have 3 VM. Okay, now about this one, we will finish.
Hello, ma'am.
Yeah.
In the previous one, in the tripler, during the first positive half cycle, won't even C3 conduct?
Yes, ma'am. I am also having a similar doubt.
Because it is uncharged, so uncharged capacitor also acts like a short circuit now. So D1 will also be short and C3 will also be short.
See, during this positive half, this is plus and this is minus here.
Yes.
Right? If this is conducting, see, this capacitor is first, it will come. This bucket is empty, it is going to fill up this first.
Yes.
Okay. And this is the only path. Because this is not and this is not.
Why is D3 not there? C3 is uncharged, so even C3 will get completely charged, and that is positive. So even D3 will become forward bias only now.
because battery is only giving VM voltage and capacitor only needs
Okay,
C1.
listen. Okay, let me tell you. See, now this is repeating. Now this cycle is repeating. A repeat cycle.
Hmm.
Okay. So now let us think that you are at the third cycle. Okay. So when you are here, what will be the voltage of this circuit?
Of the circuit,
Huh.
zero.
What will be at C1, C2, and C3? See, during this when it is starting, right? It is this C1, this. Then in the negative half, you will have this. Then
Yes.
again in the positive half, you will have this voltage and this voltage. Then in the negative half, right?
Yes.
This will charge. And this voltage will appear. It will remain as it is. So when you are here, if you put the polarity, it will reverse bias. There will be this will be reverse biased. Because this is plus and minus. This polarity. That's anti-recharge. See, when you are at this stage and they are zero is different. That is only for the first cycle. I said before also that in next it will take 2-3 cycles to settle out, and then it will remain 3 VM. Okay, so now this voltage is there. This is recurring. This is not the first. In the first pulse, okay, but in the first pulse, this is already empty. It has to fill up this. But
Yes.
then when you go ahead, these voltages are established and that will reverse bias. What do? You make a table, first half, second half, third half. And then C1, C2, C3, write down the polarity. And then write down D1, D2, D3, forward bias or reverse bias, and then show me next time.
Okay.
Okay, so this polarity will remain, which will reverse bias. In the first wave only, this is zero. But that time, this is empty. This guy this is thirsty, it is empty, it has to fill up. This will not get a chance. Even, yeah, so that is, you are right. This is zero initially, but in this first only, after it has charged. And first is happening first time only. It's not happening again and again.
So if there is any case like that, so in the first half, what will happen?
Yeah, I said no. See. Ashim,
Yes.
this is there for some time. It's not going to be forever. And then the negative half will start immediately. Okay. So during this time, this will be filled up.
So only C1 will only be filled up.
It was empty and it is now filled up with charge. By the time this guy comes, this is coming now in the picture. And this has stopped. There is no more charge to be flowing, that is flowing. And so this is now reverse biased, and this will be forward biased. And it will charge this. But forget the first cycle. The things are charging. I mean, 2-3 cycles it has charged. You do it in LT Spice, and as I said, you make a table. You say first half, second half, third half, and fourth half, fifth half. 5 cycles you do. Then you write down for C1, C2, C3, and then diode D1, D2, D3. Write down the voltages of C1, C2, C3, and then diode forward bias or reverse bias. That things will be clear to you. You should do it. And check it out in the LT Spice also. And in fact, your tomorrow's exercise is on this one.
Okay.
And I have asked you to change the when you see even the load, even the input, even the diodes also, and see how things are behaving and understand why. That's why I give more stress on why. You should know that every half what is happening. And as your question is good, it is very true that whatever comes, if this is filled, then the next one should be filled, right? But this is not remaining forever. Then there is a negative half coming. These are the AC signals. And the point is that this first half is for a little time only, right? Then when you have the other second cycle, third cycle, fourth cycle, this is established. This is established. So that will reverse bias to this diode.
Yes.
Okay, it was a good question, and I know your ID for asking a good question. So here also now you can understand that how the things are connected, right? So that's the beauty here, that the way the diodes are connected, and that's why here. So here during the second positive half cycle, right? So this will be charged. So if you go on adding more, then it will be 2 VM. So now we are adding one more D3 D4. Sorry, D4 C4. Okay, and the polarity is this polarity and this. So alternate the connections are, and we are taking across this. So during during the second positive half, right, you will have 3 VM, and in the fourth one you will have, this will be charged to 2 VM, and you will have 4 VM that is established. So during the second positive half, right, we were taking across here, and you are clear up to the second positive half, right? So what is happening during the second positive half? So I'm repeating, if you, the same thing I'm repeating, okay? If you have any problem, you can ask me. So during the second positive half cycle, now diode D3, this one, right, is forward bias, and diode D1, D2, and this D4, they will be reverse biased, okay? And diode D1 is reverse biased because of the voltage, that is the polarity, because this is plus and this is minus, and the way the polarities are, right, the way it is connected, and across C1, and diode D2 and D4 are reverse biased because of that, already the way they are connected. So the orientation of that. Okay, the orientation is this negative and positive here, and I'm talking of the positive cycle in the second wave. Okay, so already the positive cycle is plus minus, and the way they are connected here. So then what is happening? Only in the positive half this D3 is conducting. Okay, and then because of that, the voltage that is 2 VM will appear across this C. So this C2 voltage, this will appear across this C3, as we have just seen. Now we go to, so for quadruple you have to go to this stage, right? So up to the second. So up to here it is all as it is preparing itself. So here only you will get 4 times, and then it will remain. Okay, so then when you take, it will remain, but first is the preparation, right? So here, up to here, you will not get 4 times. Here only you will get 4 times. So then what is happening, that during the second negative half cycle, right, what will happen, diode D2 and D4 are forward biased. So this, sorry, control Z. So this and this, they will be forward bias during this negative and then positive cycle. Okay, as I said, you can again make a table and check it out, because of the orientation are forward bias, whereas diode D1 and D3, this one and this D3 are reverse biased. Okay, and what will happen because of that? The charge that is 2 VM stored in the capacitor, this C3, is discharged. So now this voltage appeared here. Now this voltage will appear here. Okay, so this voltage is appearing here. This is as it is. So after that second cycle, you will have 4 VA. So the capacitor now C2 and C4 are in series. So we are taking at this end. If you take here, you will get 3 times. If you take here the voltage, you will get 4 times. and you go on adding, you will get that way the voltages. So then C2 and C4 you add up, and that is 2 VM and 2 VM. That's why the total output is 4 times. And in short, you are giving VM, that was AC plus minus, but you can get 3 times, 4 times. If you add one more D, C and then D, here you will get 5 times. If you take across here, you will get 6 times. If you add one more C and D, you will get 8 times and so on. But the power remains same. If the voltage is increasing, the current is decreasing. So every diode you can check. So in the second, this half, you know what are the capacitors value. You know that this is negative, positive, and check out the polarity. Right, the way they are connected. In this half, only D2 and D4 will be conducting, and not D1 and this. And then during that half, whatever was here will appear here. Yeah, this is flowing. So this is yeah. Anyway, so many things, but not to be confused. If you understand this, it is easy to understand this, and if you understand this, it is easy to understand this.
Will there be any ground conducted here?
Wait a minute, pardon?
Is there a ground to be conducted in the circuit?
Yeah. Every circuit, if it is not shown, there is a ground, no?
So where will it be?
Okay, so when you are giving this voltage, okay, so this is positive, this is negative. So when you make a connection, wait a minute. No, all circuits have a ground. Just 1 minute. No, your question is a valid one. And here, positive, negative.
Ma'am, we can put it anywhere, right? Like,
No.
because it is just like a reference point for voltage.
No, you are right. I just don't want to come that way. Let me not comment now. Your question it has confused me also. I'll come to you next time. You are right. No, ground to ground. Anywhere is not the point. Okay. I'll tell you next time.
So for tomorrow's lab, what do we have to do?
No, I'll after my this thing, I'll give a thought and I'll leave it in the book. Don't worry. So this is a simple question, but it has confused me also. So I beg your pardon and come back.
Ma'am,
Bol.
diodes are much smaller size, so why don't we just replace the huge transformers with such long N diode
Okay,
circuits?
your question is very good. See, now you have to see the application. Now see where this voltage is in the power supply hydro. If you have gone and visited any hydro station, hydro means where from water this voltage is sent through transmission line. It comes. If you go there in the hydro station, you will see big transformers. Okay, step up, step down, and all those things. Because those are very high voltages. Okay, now so see where you need hundreds of voltages, a diode will destroy. Okay, so there you will see very, very big transformers. If you ever visit, you can inquire and ask and out of your curiosity and see. Now, the same thing as I explained you in the beginning, we can use using transformer also. But transformers in where our applications are, if you can do the same thing with diode, we will prefer diode because it is less heavy, less expensive, and packaging and everything. So if you want to make a TV and you need in your CRT or as for a black backlighting of the LEDs that are used, if you use transformer, it will be really, really bulky and heavy. Okay, you understand my point? So this is an alternate where you are at a win-win position, but this diode will not work in that hydro station. Even a very strong diode, if you make, will not work. Then you have to make very, very big diodes. Now that is the transformer is a better this thing there in hydro. So these are semiconductor devices which are not working at hundreds of volts, in short. Shall I?
Yes, ma'am.
There it is hundreds of volts there. And then how you will do? So these guys will not work. These are tiny devices. Okay. So after my lecture, I'll come back to that thing. No problem. Anyway, it's a simple question, but I'll run it on LT Spice and come back to you. So the next chapter is bipolar junction transistors. Okay. And now we are with the transistors. Diodes main application is as a rectifier and voltage regulators. Your LEDs are diodes. So now even your bulbs and they all work right on this principle. So the point is diode, there are some special applications where we cannot work without diode. So, and there are things for every application, right? If you need a rectifier, you will use a diode. If you want to make a switch, you can make a switch with a diode, right? But we will use, when you say switch means digital application, and when we make digital applications, right, you can use diode, but digital means, again, when you make a circuit, it is area. In digital, it is not only area, delay and power, there is also something like noise margin. And another thing that you must understand is that when you make an application, it will have both analog and digital, both the signals, right? It has to process. So for example, if I'm talking of an embedded application, then you will have a sensor. And even if I'm talking now, there's a microphone and the amplitude is very low, right? And it has to amplify. So all the stages you may have to filter, right? And then if you want to now, if your computer, if you want to do some processing on the speech, or any analog signal, you digitize that and you use some equations, right? You save it, it's all digital. Now, if you compare, I have talked before that when you design an application of the total area or, the digital is like 80%. And analog is 15 to 20% of your whole application. You divide into analog and digital. No application is just digital or just analog, because when the signal is generated, it is analog. You convert A to D converters are there to convert into digital domain and all, right? So with that thing, my point here is that if you are using, let's say 50 to 100 transistor to build your whole analog, there are hundreds of transistors to make a digital circuit. And so you can understand the computation. Digital is mainly for computation and the storage and all, right? So you need a lot of transistors, and if all those transistors are working at the same time, or let's say even 50% of that, And if you calculate the power, right, it will use a lot of powers. Analog compared to that, your digital circuit, it has to process more, and the power requirement is high, demanding. So if we don't make circuits that are robust, so as an engineer, we have to just make sure that it uses minimum power. Okay. Another thing is that your signals may be subject to variation, and another signal which is passing in the vicinity may also change. There may be noises. So your zero can be flipped to one, your one can be flipped to zero. So to make all these things, the ideal one is a transistor, where a transistor can be used to make a circuit digital as well as analog. And in analog, amplifier is the main thing. And in digital also, we will see the simplest one is inverter, then the NAND and NOR, and like that. Okay. So two domains. As I said, it takes more effort to understand analog, which is really challenging if you don't understand the basics. Even if you want to make just use one or two transistors, right, it is challenging because you have to understand the transistor and how it works, and how to give the voltages, and what is the requirement, and for that how to make all connections. You have to use R, C, and all those things. Whereas in digital, if you learn digital, you can teach also. Well, just learn and you can teach. Okay, so and for as an engineer, it's all about design and analysis. You have a, okay, you know that from this microphone I will get a signal of this range, and I have to, if you I want to generate or regenerate at the speaker, then also you will need an amplifier there, and to process this signal, because these signals are very weak, and it has to, you want to process it, it has to pass through the circuits. Okay, so while passing, like, you know, when we are walking, our energy we get exhausted. So this signals also die out. Okay, so they have to be strong enough that they pass from one stage to another stage. And in addition, it is like filling up your, you know, when you are on a long drive and you have to fill up your tank, right? Your car, ki bhai, taki full kari, you make it full. So that way, you have to give energy. So every circuit has a bias. So that's where you give the energy and make your electrons move. So energy, of course, we give by biasing, but even after giving that, also your signal should be strong enough to propagate, right, in that device. So there are all these things. I'm just explaining in a layman way, but we have to do it and apply this to circuits. So we will extensively learn about amplifiers, and to understand how to amplify, you have to understand the device. And another thing is stability. So even if you make an amplifier, it should, we have to ensure that it does same amplification, even if there is a change. And now the changes can be in the voltages, right? It may happen that there are fluctuations in the voltage. Sometimes the temperature can change. Now all these factors will affect the working of the device. Like in the diode, if you remember, we had seen that with the change in the temperature of one, if to recall, I can show you, I have it open here. All right, so if this is changing, right, even with a little change in temperature, then you must understand that this will affect the amplification also. 10 times if it is amplifying, it may amplify only 5 times, and then what? So your signal is always dancing, kabhi up, kabhi niche, kabhi upar. So it is not being reproduced the way it is, right, like the original signal. So we have to make sure that it is stable enough. And for that also, to get stability, like in the life also, to get stability, we have to work more hard. So in the circuits also, to make it stable, you have to add something, right? To add something, you have to then understand. So there are all these things there, which we will see here. And just an introductory first to start with of this device, which is very essential you to make a circuit. You have to understand the physics. Okay. So as an engineer who is into design has to understand the physics also, has to understand the electronics also, has to know how to simulate and all those things, right? So here we are studying BJT. Now in today's date, now these BJTs are used in power supplies, right? Because see, now this is a transistor, and in today's date there is another transistor that is known as MOSFET. Okay, it was replaced by MOSFET. So when this guy came, it's like a big brother, it was all alone, and then it was followed by a MOSFET, which is also a transistor, but the dimensions of this are in micrometer, that is 10 raised to minus 6 of meter. This is the dimension of the MOSFET. And the BJT, as we had shown you in the lab, you can hold it in your hands like a resistor, capacitor, right? So this is a discrete device and it has dimensions in millimeters. So this is really big compared to its counterpart MOSFET, which can be fabricated in an integrated circuit. So that chip you see has millions of MOSFET. But this BJT is really big. You can have 2-3 BJTs of the same. If you combine BJTs, it will be just 2-3 of the same area of the MOSFET. So now, as you can understand, bigger the size means it will handle more voltage and more current. So in the applications where you need even higher voltages and current that a MOSFET cannot satisfy, we use BJT. So mostly in the power supply, right? Because these MOSFETs are of the order, in today's date, MOSFETs work at the order of 1 volt. If you need 15-20 volts, right, then what we'll do, we'll use BJT. So these are high voltage, high current devices, transistors compared to a MOSFET. And not every, because MOSFET is more ideal for digital applications. In today's date, we also have MOSFET that can tolerate high voltage and high current, but this is by nature, BJT is handling this. And if you want to use those kind of MOSFET, they are really, really expensive, because then you have to make it in a chip using the latest technology, and that is even challenging. So if you are making a TV unit in that, or a refrigerator or whatsoever, your power supply, there is a power supply in each and every, in your laptop, everywhere, where these BJTs are used. And in analog circuits, it's not, you don't need hundreds of, you need couple of transistors, right? But it is a challenge to design a circuit in analog domain. So this bipolar, from the name junction transistor, is that it has a junction like a BJT, sorry, like a diode, and it is bipolar, means there's both the polarities, that is current, and the current is because of the electrons and the holes. Okay, so it is bipolar. Here the game is all about generating the current by giving a voltage, and but to understand, to get a current is your signal that is propagating, and your voltages are your signals input. Your input can be a current or a voltage, and current when you take across, or when you have a load and the current is flowing, a voltage is established. So they are like, you know, I mean, current gives rise to voltage and voltage gives rise to current, right? So that way it is. So here, if you see, this is the basic structure of, you are all listening, right? And understanding what I'm speaking.
Yes.
Okay. So see here, if you see, this is, you can, this I'll come later on. This is NPN. So this is like 2 PN junction diodes connected back to back. Okay. So NPN, and these are 2 diodes connected back to back, which gives rise to this kind of structure, we can say, and this is basically your BJT. how you differentiate is that this part is an emitter region, then a base and a collector. Emitter, from the name you can understand that this is going to emit. If it is n-type, the majority of the carriers are electrons. Similarly, this is hole and again electron. And here the current moves from here to here and here to here, but the majority emitter is a pull. It is emitting electrons. Okay, so it is an emitter. The collector, from the name, it will collect. So, and this is a controlled way. If you see this, right, the current is flowing, and this is a controlled way that you can stop the current to flow or it will flow more. Okay, and that is, it can work as a switch. And what is more important is that this is like, a small a processing unit, you can say. It's not a processor. We make processor using these devices, but what it is processing is, as I said, voltage gives rise to current, current gives rise to voltage. In this case, so when you have your input in terms of voltage, okay, so in digital circuits it is 0 and 1, in analog also we will see all this. So this current is generated because of the voltages you give. And since, as you can see, there are 3 terminals here, right, we can give 2 voltages. 2 voltage sources are needed. Okay, so voltage sources is plus or minus, and here there are 3 terminals, so we'll be using 2 voltage sources. One voltage source will emit the electrons here, right, and they are emitted and they are lying there, but they are not running. If they are moving, then and then you say, and the electrons are moving, then and then you say a current is generated. But there may be many electrons. If they are not moving, current is not generated. Okay, so this is just emitting and collecting the electrons and all. But the potential here will suck the electrons. It will compel it to move. Okay, so it is going to suck the electrons like a vacuum cleaner. So you need one to emit, and you have a pool of electrons to generate. Because if you don't generate electrons, you will not get current. Then what you will make to move, right? So first you generate, you need a voltage to do that, and then to accelerate that, to make it run or move, you need another voltage source. So basically 2 voltage sources you need. Okay, and since we have 3 terminals, what you will have is that you will connect. This is emitter. So this junction is between, so there are 2 junctions, as we just talked, junction transistor. So this is between the junction between P and N type. So like now you know this diode. So this is emitter base junction. We say abbreviated as EBJ, and then this is CBJ, another junction established here, and we give a voltage across these terminals. Okay, between this and this, and we give between this and this. Okay, or we can, if you give some voltage here and then some voltage here, you can also find out what is the difference between emitter and the collector, and there are conditions. Okay, so with 3 terminals and 2 different voltage sources, you have now you have an option to connect the polarities, because there are 2 voltage sources and each has 2 polarities. So there are 4 different options that you can connect those voltage sources to these 3 terminals. And it depends on if you connect some in the A, B, C, D, let's say 4 different ways, 1, 2, 3, 4. If you connect in one way, right, so that is this is forward bias, this is also forward bias, this is forward bias, this is reverse bias, both are reverse bias, this is forward bias, this is reverse. So you have 4 possibilities, and the way you connect, it will operate different ways. Okay, so is that much clear to you? There's another brother of this is N-type, this is NPN we say, and there is another flavor that is PNP. Okay, I'll explain you tomorrow what is the significance of this PNP, and both are needed. So based on what I explained you today, we'll go ahead. But as I talked, if we just concentrate on this type, right, it depends on how you connect. So you have EB junction and CB junction. So you have this junction and you have this junction. And the way you connect, if this is forward bias, both are forward bias, then what? So this both junctions, both are reverse bias. This is forward, reverse, reverse, forward, forward, forward. So then depending on how the connections are made, you have different modes of operation. Okay, and if you want to make it use as a switch, okay, then you have to operate it in cutoff and saturation. If you want to use it as an amplifier, then you have to make it in active mode, meaning that your EB junction is forward biased and your CB junction is reverse biased. And for all this, there is a physics. When you bias in a particular way, there is some physics happening, and that I'll explain you next time. And I leave that that ground thing. Good question. I'm just leaving it. I'll do it in LT Spice and I have to check it out with proper reasoning. Okay. So I come back to you in some time. Any questions up to this? If you have, let me know. I can explain you with regard to BJT. We have just started, but these fundamentals are very important. Yes.
Madam, you said that the collector will suck the electrons. I did not understand how it will do it.
You just bear it up to my next lecture. Hai? See, I just explained you in a layman way. Okay, but that is the functionality. See, okay, let me explain you in that way only. In detail, we'll see by all these other things later on. See, what is this basically? This is like a processing thing that, you know, you are giving, see what you want to process your information. What is your information in form of, if I'm speaking, my words will not flow through this. It is the current which will represent my voice. Now, here it is all current and voltage. Are you getting me?
Yes.
So circuits, it is current and voltage. If you want my voice to be converted into current to process it, so how it is, you are listening to me, but how it is happening, microphone will convert the acoustic into that. Then there is a black box. So let's say there is a microphone, right? There is a microphone, some like so some microphone is there, right? It goes, so now it goes to that black box, let's say. And on the other hand, there is a speaker that you are listening to. Okay, so there is a speaker at your side, and this is microphone at my side. Now this microphone signal is converted into electrical signal. So this is a black box and you are able to listen there. So this half processing will happen at my side. It will come to your